welcome back. Alright, discrete random variables. So this is just going to be part A on this chapter, because the first little bit's going to match up for HL and SL. You'll see there's a couple of little extra things the HL students will do there. Talk about that in the HL video in part 2, and then we'll all be back together for part 3. Alright, so first little bit, random variables, discrete probability, distributions, and expectation. Let's have a look here and see what is going on. So I think we've got a good idea about the difference between a random variable and a non-random variable. Random variable uses numbers to describe the possible outcomes which could result from a random experiment. We've been doing that for years. Continuous and discrete. Continuous can take on any value in a particular domain, although we usually measure it to a certain degree of accuracy, so that is some limit on it. But in theory, something like a length or a distance, a time taken to complete something, a continuous value could end up anywhere in that domain. Discrete values, only certain values are possible. Number of people in this room, number of runs scored, number of points in a game, those sorts of things. Discrete values, there are certain values and only certain values that you can have. That's a different situation. That's discrete. Continuous can take on any value in the domain. I'm sure you know that. So discrete probability distribution, something like tossing two coins and seeing the number of heads you've got. Who's ever seen that before, I wonder? Okay, and there's different ways of representing that data there. Uniform discrete random variables, everything has the same probability of an outcome. If I just tossed a coin once, heads or tails with a probability of a half for each would be an example of that. Rolling a six-sided die, the probability of a 1, 2, 3, 4, 5 or 6 is all 1/6. Finally, discussing the mode and median. The mode of a discrete probability distribution is going to be the most likely outcome. When I'm tossing two coins, that's one head and one tail. When I'm rolling a six-sided die, there is no most likely outcome, so having 6 modes isn't really a thing, so there would be no mode. The median is the distribution corresponds to the 50th percentile. So to do that, you take each score, you figure out the probability of the lowest score. Of course, you're arranging them in order, and once your probability reaches 50%, that's the value that is the median. There's a little example underneath here. Hopefully I didn't scroll too far. So a magazine store recorded the number of magazines purchased by its customers in 1 week. Let's just zoom in a little bit, make it easier for you while you're watching along. 23 purchased 1 magazine, 23%, 38% purchased 2 magazines, 21% 3, 13% 4, and 5% purchased 5 magazines. Let X be the number of magazines sold to a randomly selected customer. So here's an example of using past information to tell us and inform our decisions in the future. So here we've got 1, 2, 3, 4, or 5 magazines purchased. Remember, these were the number of magazines purchased, so there's no 0 because we're not including people who didn't purchase a magazine. The probability, so 0.23, 0.38, 0.21, 0.13, 0.05. Is this a probability distribution? What are the things we need to check? There are always 2 things we need to check. First, you need to make sure that the sum of the probabilities adds up to 1. Let's have a go. 23 and 38, 61, 82, 92, 3, 4, 5, 100, so 1.00. That's looking pretty good. Second thing you need to do, make sure none of the probabilities are negative. None of them are negative here, so we are good to go. This is definitely a probability distribution here. What other questions have we got? Oh, there's our probability table. Graph the probability distribution. I'm sure you're all more than capable of doing that. You can do it on your calculator as well. And find the mode and median of X. Again, possible to do on your calculator, but I think this is fairly easy for you to do straight away. The 50th percentile, if I want to find the median, 0.23 plus 0.38, that's getting me above 0.5, so the value that was at exactly 0.5 must have been 2, so 2 is going to be the median. The mode is also going to be 2 because you can see that that was the most likely occurrence. So customers are most likely, so this is the mode, and then they talk about the median is also 2. Again, pretty straightforward. We've done that sort of thing before, nothing too controversial there. We can also describe the probability distribution of a variable using a probability mass function. Fancy name for saying this function could describe the probability. The area under this function is going to equal 1 for discrete values, because the area of those rectangles, when I add them up together, will equal 1. The probability of 1 is 2 over 34, probability of 2, 5 over 34, 3 is 10 over 34, and 4 is 17 over 34, according to this rule here. Do I have a probability mass function? What are the two things I need to do? 1. Do the probabilities add up to 1? 2 and 5 are 7, and 10 is 17, and 17 is 34. 34 over 34? Yes, the sum of the probabilities is 1. Are any of them negative? No. So, each of these values, also none of them are bigger than 1. There's another important point, but that would be ruled out by having them add to 1 and having nothing negative. But that's the way they've expressed it there. All the probabilities are definitely strictly between 0 and 1 inclusive, and the sum of the probabilities is equal to 1. So yes, it is a probability mass function. Last thing, what we can do, we can use these to determine expected values. Expected values often going to come up in sort of gambling, that sort of thing, but also you might be calculating expected return based on different scenarios that you've predicted for your business, so it can be very useful here. Here's a spinner alongside, 5, 10, 15, and 50. The probability of each one there would be a quarter. How would I find the expected value? Well, the probability of the result 5 happens 1/4 of the time, so I'm going to have 5 times 1/4. The result 10 happens 1/4 of the time, so I'd add to the 5 times 1/4, 10 times 1/4. Again, I'll add 15 times 1/4, and finally add 50 times 1/4. And we go ahead and add those together. You can see they're doing it here. They factorize out the quarter. Seems like a good idea. The expected value, the expected number of points scored spinning that spinner is 20. Note, and they even noted here, you can't get 20. The expected value is not necessarily one of the values. It is the long-term average if you did this a number of times. So the more times I spun the spinner and wrote down the value, assuming the probabilities are correct, the long-term average of those spins is going to approach 20. So that's a little summary of the rule. The expected value of X, you just add up each score multiplied by its probability. Nice and easy to do. Finally, fair games. The expected gain for a player or for the person running the game should be 0 for it to be fair. There's a little talk discussion point there. Would you expect a gambling game to be fair? They're not going to be fair, are they? The thrill of gambling is getting a win against the odds, so that's what people rely on. But the people running the games have to make sure they don't go bust, so they make sure the games, the long-term average of those games is going to be stacked in their favour. That's what's going on there. I'm going to leave this first video here. That's a little introduction again. I think you know most of that. Have a go at a couple of questions from each exercise. I think you'll be okay with them. I'll come back in part 2 and part 3. See you then.